Okay, in this series of videos, we're going to be exploring Lagrangian um, mechanics. Now, this isn't like as opposed to Newtonian mechanics. What you can show, and in fact, over the course of the next couple of video series, we will show, um, if you assume the truth of the one, you can derive the other. So you can kind of take your pick which you consider more fundamental. Certainly in the world of high energy physics and quantum mechanics, the Lagrangian formalism and its cousin Hamiltonian mechanics reign supreme. Um, but certainly you can choose one and derive the other. There's no real saying which is more fundamental, at least at this point. Okay, so what we're going to take a look at in this video is the concept of a generalized coordinate. So to do that, we're going to need to look more carefully at constraints. And so I think it'll be instructive if we just plain think about a pendulum hanging on a string of length L, happily oscillating in a plane, like so. All right, so if we were working in our normal Cartesian coordinates, we would give the position of the bob as an x, y, z coordinate triple. Now, if we think about it here, the motion of the bob is subject to some constraints. I said it was oscillating in a plane. That may as well be the z equals 0 plane. So one of our constraints is that at all times z has to equal 0. Another constraint we have is that we're not going to allow the string to stretch. So that means we demand that x squared plus y squared equal L squared. Now these constraints are examples of what we call fixed, or the fancier name for it is scleronomic, S-C-L-E-R-O-N-O-M-I-C. Can probably win some bets on that one. Holonomic will define all these in turn constraints. So we'll define all this better in a little bit. Now, if we look at these constraints, sure, we are describing our position of our bob in xyz, but we already know z equals 0 for sure. And this constraint, if we knew x, we get y automatically, or vice versa. So really, we only need one variable to describe the position of the bob. And there are two choices that are logical. I'm sure there are plenty of other choices, but there are two really obvious ones. One is we could go with the arc length, S, that we are from equilibrium, or we could go with theta, the angle that the string makes. Likely with vertical. Either of these would be considered examples of generalized coordinates. So rather than demanding xyz or r theta phi or something like that, all we need is just some variable that gives us an unambiguous recipe for figuring out where the thing is. And we call that a generalized coordinate. So, how many generalized coordinates do you need to describe things? Well, if you have n particles and m holonomic equations of constraint, the number of degrees of freedom in the system, S, is equal to 3n minus m. And you will need S generalized coordinates. So let's just do a quick example with that. Let's take a look at a dumbbell. So we got two particles, particle 1, particle 2. We'll draw in some coordinate axes like so. We'll say this angle here is theta. And we'll say if I project this down that this angle is phi. Okay. All right. So we have one constraint. And that is that we demand that x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared be equal to the squared length of the rod that holds them together, massless rod that holds them together. So we have two particles and one holonomic constraint. So S equals 3 times 2 minus 1 equals 5 degrees of freedom. So that means that you need, in general, 5 generalized coordinates to describe it. I already kind of gave away 2 of them, the theta and the phi that I already drew. But a good set here would be to pick the capital X, capital Y, capital Z, theta, and phi, where this is the coordinates of the center of mass. Then theta and phi show the orientation of the dumbbell. All right. So that would be a logical set. I'm sure you can come up with others, but that's the one that I would go with. Okay, so the moral story is we can reduce the number of degrees of freedom if the constraints are all holonomic. So this is a good time to get into the kinds of constraints there are. So there's holonomic constraints. A holonomic constraint can be written in the form of saying that the jth function, you can write it as some function of the coordinates x, y, z, I, and possibly the time. And we can set it equal to 0. And we're letting I run from 1 to the number of particles and j run from 1 to the number of constraints. So if we can write it in this form, it's holonomic. Now, if there's no explicit here, let's rewrite that. If there's no explicit time dependence, then that is a fixed or scleronomic constraint. Implicit time dependence is okay, but no explicit time dependence. If there is an explicit time dependence, then it's called a renomic constraint. All right. The other major category are non-holonomic constraints. A non-holonomic constraint is literally one that can't be written in holonomic form. So for instance, if something is demanded to be outside of some sphere of radius L or something like that, we could write a constraint of something like x squared plus y squared plus z squared minus L squared had to be greater than or equal to 0. Since that's an inequality, that makes a non-holonomic constraint. Those are beyond the scope of this course, although you'll probably hit up with them a bit in graduate school. Okay, so now that we got the idea of generalized coordinates down, we will want to extend the idea here so that we can express the kinetic and potential energy in terms of generalized coordinates. Generally speaking, you've got two strategies that you can do. One is to write everything down in Cartesian, and then use transformations to take it into your generalized coordinates. Choice 2 is you work directly in the obvious, in your generalized coordinate, and you use something like t equals 1, you say t equals 1 half mv dot v, and you go ahead and you construct your own unit vectors. So let's say you construct e's. You follow the same kind of recipe for the potential energy, but it can often be expressed naturally. And we'll get some examples of that going in just a sec. So one example that we could go and look at would be our friend the pendulum again. So there's my ceiling, there's my bob, there's my string of length L. All right, so the obvious generalized coordinate here is theta. I suppose you could use arc length, but why? So we'll go ahead and do method 1 here first, just to get some feel for how that goes. So we'd be writing that the potential energy, the kinetic energy, sorry, is 1 half m x dot squared plus y dot squared, or 1 half m x dot squared plus 1 half m y dot squared. And we can write that that the potential energy is minus mgy, because I chose down to be positive. All right, so here we start doing some trig, and we can write that x is equal to L sine theta, and y is equal to L cos theta. That's good. So then that gives us that x dot will be equal to L derivative sine is cosine, take derivative of what's inside, L theta dot cosine theta, and y dot will work out to be minus L theta dot sine theta. So let's just go and stick all those into our expressions here and see what we get. One choice, so we get 1 half m L squared theta dot squared cosine squared theta plus 1/2 ml squared theta dot squared sine squared theta. Oh hey, sine plus cosine squared is 1, so we get 1/2 ml squared theta dot squared, which you could probably just intuited anyway, because you could say, hey, that's the rotational kinetic energy of a point mass constrained to orbit at length L. And then for the potential energy, just plugging in, we get minus mgl cos theta. Super. Okay, method 2. For method 2, this is what I mean about the potential energy coming naturally. You would have probably just written that immediately. So we'll just go ahead and say we did. So that's what I mean about being natural. And then for the kinetic energy, we could write as 1/2 m v dot v. So it'll be 1/2 m, and then we're moving, it'll be 1/2 m r theta dot times e theta hat, right? Dotted with itself, r theta dot e theta hat. And the dot product will be 1/2 m r squared theta dot squared. Yay! Just as before. All right. Let's go ahead and do one more example to close out this particular video. Let's say we have a particle in a central force field. Constrained to move in a plane. All right, so you can write our constraint. That's z equals 0. So we have one particle, so that means we have 3 times 1 minus 1 equals 2 generalized coordinates, so it seems like plane polar. Coordinates would probably be really good generalized coordinates here, so r and theta. So intuiting it out, you would immediately write that v equals just some v of r, because that's what we mean by a central force. Now you can write your velocity in general as some er times r dot plus some e theta times r theta dot, much like we did before with the pendulum. So then we can say t is 1/2 m v dot v. So it'll be 1/2 m er r dot plus e theta r theta dot dotted with itself. All right, so we do that, we get 1/2 m times, from here we'll get an r dot squared plus, the cross terms won't matter because the unit vectors are perpendicular, so we're left with these guys here, plus r squared theta dot squared. And there's your expression for the kinetic energy. Okay, in the next video, now that we've introduced those concepts, we're going to go ahead and introduce Hamilton's variational principle and use that to come up with Lagrange's equations of motion.